I'm going to talk about obtaining optimal multipath lower bounds for one of the fundamental graph problems, namely minimum spanning trees in the dynamic streaming setting. This is joint work with Separasati and Diller-Co. So let's get started. So initially, you have a n-vertex graph, and the edges of the graphs are given to the streaming algorithm one at a time. Each time it gets either an insertion to add a new edge between U and V with a certain weight W, or a deletion which removes some previously added edge between UV with weight W. And at the end, the streaming algorithm wants to solve the minimum spanning tree problem on the final graph. And there are two different variants. In the search version, the algorithm needs to output all the edges of some MST. Well, in the decisional version, it's only required to decide whether the weight of MST is at least some given threshold T or not. And what we care about is how much space is needed if the streaming algorithm is allowed to process the entire stream up to a total of P times. And since this is one of the fundamental graph problems, it received quite some attention in the community. So for unweighted graphs, in which the search version becomes finding an arbitrary spanning forest, there's a n times log cube n upper bound, even in the seminal work of Druha and McGregor in 2012. It is also the paper that started the using linear sketches to give dynamic graph streaming algorithms. And later on in 2019, Nelson and Yu proved a matching lower bound for this particular problem. And for the algorithmically easier decisional version, which is just checking the connectivity for unweighted graphs, the same upper bound applies, and Sven and Uju proved a almost matching n times not n lower bound, even for insertion-only streams. So, however, for the weighted version, there's only a n to the 1 plus order of 1 over p upper bound for p-path streaming algorithms, given in the same AGM paper. So since then, there's almost more than a decade of time. There's very little progress on this MST problem. So we give an explanation to this phenomenon in this paper by saying that so this upper bound is essentially type for any number of passes. So specifically, we show that any p-path algorithm needs at least n to the 1 plus 1 over 2p minus 1 space to solve MST for either the search version or the decisional version. So in particular, this implies that any sim streaming algorithm needs at least log n over log n passes. Okay, in the rest of this talk, I'm going to give you a high-level overview of how our proof works. So let's first start with the search version. So the proof is quite similar to other streaming lower bounds, in which we reduce the streaming problem to some computation problem where we have many tools to prove lower bounds. So the construction is as follows. We have about n over 2 the bottom vertices, which are fully connected by zero edges. And we also have another n over 2 top vertices, where the ith vertex is connected to some bottom vertices j with an edge with weight j. And later on, we're also going to remove a subset of these inserted edges. So here, the red edges will be first inserted and later removed. Well, for the blue edges, they're only inserted, but not removed. So we can see the MST of this particular graph will have a very special structure. That is, it always contains a spanning tree for this clique at the bottom. And for each top vertex I, it will pick the blue edge with the minimum weight. That is the minimum weight edge that is not removed ever. So if you're familiar with the connection between streaming algorithm and computation problems, let's say this actually reduces the streaming MST problem to essentially a direct sum of a simple two-party computation problem where Alice holds a set A and Bob holds a subset B, and they want to find the minimum element in this difference A minus B. And it turns out this problem is a variant of a well-studied family of computation problems called universal relation. So in the original version, Alice holds a set A of some universe M, and Bob holds a subset B, and they want to jointly find an arbitrary element in the difference A minus B. So in 2019, Nelson and Yu showed a one-way commutation law bound for this problem and used it to prove the n times log cube n space law bound for streaming algorithms for finding spanning forest that I mentioned previously. And later on, we defined a decisional version for this problem and showed a similar one-way commutation lower bound and used it to prove lower bounds for connectivity, although it's only for the distributed sketching model, not for streaming algorithms. Okay, for us, what we have is actually the main version of universal relation, where instead of finding an arbitrary element in I minus B, we ask for the minimum element in the difference. So by the reduction I showed previously, so it's sufficient to show a round versus computation trade-off for this mean version of a universal relation. Okay, so just a bit more details for the proof here. So we actually do this by a reduction to another computation problem we call augmented tree pointer chasing, which is roughly the standard tree pointer chasing problem, augmented in a way that is quite similar to the augmentation we do to the index problem. So there are some subtleties in the definition, but I won't go into the details here. I just want to mention that by some very standard information theoretic round elimination arguments, we can do the work here. And after that, if we apply some existing bounded round, direct sum, or direct product arguments, we can amplify the computation to like lower bound the computation for computing multiple instances simultaneously. And also, I want to mention that the same construction here also works for obtaining a lower bound for computing the weight of MST, but it only works with exponential edge weights. As you can imagine, so we need to assign exponentially increasing weights to different instances so that the weights of the edge we pick from different instances will not mess up with each other. So like we can recover them from the weight of MST. Okay, so if we want to extend this argument to obtain lower bounds for the decisional version of MST, we can similarly define a decisional version of the mean universal relation problem, where instead of finding the exact minimum element, we just want the parity of this mean element. So it's not hard to modify the augmented tree pointer chasing problem to be Boolean and prove a lower bound for this decisional mean universal relation. And the challenge actually comes when we try to use this lower bound to prove the decisional MST lower bound. So to see why, let's go back to this construction here. So let K to be the number of instances, that is also the number of top vertices here. So, and EI is the main element in this AI minus BI for the ith instance. And let ZI be the parity of EI. So suppose we define the threshold T to be the summation of all EIs minus half of the summations of all ZIs. Now we can see the weight of MST is always between T plus minus K over 2. This seems to finish the proof because, okay, we only need to decide whether more than K over 2 instances have answer 1 or not. So this is essentially computing the majority of the answers of these K instances. But not quite yet. We have at least a couple of issues. So first of all, this value threshold T is not fixed. That is, it depends on the specific instance here. So it's not a predetermined value that I can give to the streaming algorithm as part of the input for the decisional MST problem. So to overcome this, we can just add an additional edge, the green edge here, with weight equal to some large enough constant minus t. So this way, the MST weight will always be between some constant c plus minus k over 2. However, this additional edge actually leads to another issue, that is, it correlates the k instances here. So if you're familiar with direct sum arguments, we always work with independent instances. So in order to get rid of this dependence introduced by t, we can just make a random guess at the value of t. So if this guess is correct, we just proceed by ignoring this t, or like pretending we don't have this t. Or if the guess is incorrect, then we just output some answer uniformly at random. Okay, so far we have independent instances and also a fixed threshold. Are we done if we have some sort of majority lemma? So the answer is unfortunately no. This is because this random guessing of t actually reduces the advantage of our protocol to roughly 1 over poly k, because the value of t can be as large as polynomial in k. So I'm going to show, so majority lemma will never hold in such regime. So to see this, let's consider the following protocol, which takes k instances and just run the one instance protocol on the first instance and output its answer as majority. So by the properties of binomial distributions, we know the probability that the majority will be equal to the first instance is roughly half plus 1 over root k. This means if we have a protocol for computing a single instance with constant advantage, we can also get a protocol for computing the k-fold majority of k instances with the same amount of computation and roughly 1 over root k advantage. Or in terms of hardness, if we know it's hard to compute a single instance with seed computation constant advantage, we cannot get the hardness for the k-fold majority with roughly the same computation and 1 over root k advantage. So we don't have this majority lemma. So the workaround is actually the following kind of a small trick, which computes the k-fold XOR from the k-fold majority. So in particular, consider the protocol which first computes the majority of the k instances, and then output the parity of k over 2 if the majority is 0, or output the parity of k over 2 plus 1 if the majority is 1. And again, by properties of binomial distributions, we know the probability that XOR will be equal to the parity of k over 2 plus majority is also roughly half plus 1 over root k. So this means a protocol for k for the majority with roughly half advantage will imply another protocol for k for the XOR with the same amount of computation and roughly 1 over root k advantage. So how are we going to use this small trick? Let's consider the following chain of reductions. So at first we have a streaming algorithm which computes the decisional MST. And by our reduction, the construction I gave previously, we can get a protocol for computing the k-fold majority for the decisional mean universal relation problem with this value t and some constant advantage. So if we repeat this protocol log k times, we can boost the advantage to roughly half minus 1 over k. And now we apply this small trick, which reduces the XOR computation to majority computation. So we now get another protocol for computing the k-fold XOR with roughly 1 over root k advantage. And only at this point, I'm going to randomly guess this t so that we can get rid of this correlation between the instances. This step reduces the advantage to roughly 1 over poly k. And now, suppose we have some sort of XOR lemma as opposed to the majority lemma, okay? So it will give us a protocol for computing single instance of the decisional mean universal relation problem with roughly 1 over k times the computation and constant advantage. So let's take a further look at this chain of reductions. At first, we have a protocol for k for the majority, the computation, and constant advantage. So suppose we have some XOR lemma. At the end of the chain of reduction, we get another protocol for computing a single instance with roughly c over k computation and also constant advantage. So we can see this is essentially a very weak majority lemma. So I'm saying weak because we're only getting like constant advantage here instead of like 1 over root k or even 1 over polynomial or exponential in k. So if we rephrase it in terms of hardness, so if we know it's hard to compute a single instance with some computation and constant advantage, then we can also get that it's also hard to compute the k-fold the majority of the same problem if we get like roughly k times the computation and we also want like constant advantage. This is like exactly what we want for our streaming lower bound. It's a weak majority lemma, but it's still sufficient for our purpose. So finally, it remains to show the existence of good enough XOR lemmas. So fortunately, in 2022, you proved the existence of such an XOR lemma where like the computation increased by a factor of k over r to the order of r, and the advantage to k is exponentially in k. So if we plug in the numbers, we get a space lower bound of n to the 1 plus 1 over 2p minus 1 divided by p to the order of p. However, we can only get such a bound for number of passes up to at most square root of log n over log n. So there is still a gap between this lower bound and the upper bound, which is log n over log n. So to bridge this gap, so in our paper, we actually improvised a multi-party XOR lemma. So roughly speaking, we have two K prime parties. So there are like K prime pairs of two parties. And each pair will hold roughly K over K prime instances. So you can also view this at a high level as a streaming XOR lemma on top of a direct sum argument for each pair of parties. So this way, we're able to show an XOR lemma in which the commutation increases by a factor of k over k prime divided by r, and the advantage decays exponentially in k prime over r. And we plug in the numbers and get a space lower bound of n to the 1 plus 1 over 2p minus 1 divided by polynomial in p. And this is sufficient to get the optimal pass lower bound of log n over log n. And also as a final note, I also want to mention that in a independent work by Iyer and Rao, which is also accepted to STOC 2024, they actually improved use XOR lemma by showing that we can actually increase the communication by a factor of k over r. And the advantage still decays exponentially in k. So if we directly apply their new XOR lemma, there's no need to work with the multi-party setting anymore. And we also get like slightly better dependency on P and log n as a byproduct. Okay, and that's it for the talk. And these are the references.